Hi everybody. Here's what we're going to do. I'm going to show you guys how to do the displacement versus time graph for your marble acceleration lab. And we're going to talk a little bit about the equation that you're going to get from that graph and what to expect from it. Then in a separate video, we'll talk about the velocity versus time graph because that one involves a little bit more calculation and is going to take an extra minute and a little bit of work. So let's start with displacement versus time. All right. So as we look at our data, we're going to find a few things about it. All right, so as we do displacement, which we're going to measure in meters, versus time, all right, which is going to be measured in seconds, we're going to notice the data is going to follow a certain pattern. Now remember, we have this ramp, and we're going to roll a marble down the ramp, right? It's going to go down, it's going to reach the bottom, and what we're doing is we're measuring the time that it takes to reach the bottom there. At the same time, we also know its displacement, delta x. Now, as we bring this marble farther and farther and farther up the ramp, what it's going to do is it's going to accelerate for longer and longer and longer. But the acceleration is going to stay the same for the entire time, all right? What we're going to notice is that it's going to pick up speed. It'll be traveling faster at the bottom of the ramp each time we move it farther and farther and farther up the ramp, all right? The goal of this lab is to find the acceleration. So what is the acceleration on this ramp? And we're going to do it two ways. The first way is by using this displacement versus time graph. All right. So here's what happens. We collect this data and we're going to notice a pattern to it. All right. The pattern is going to show that this is actually going to follow a bit of a curve. All right. So just looking at this data, we might think, oh, maybe it's a little bit linear, but when you do your data, it's actually going to look a little bit more like this. All right, so as I did my displacement versus time graph, okay, so I have all of the times, and I made up stuff, all right? I made stuff up here for this data set so that we could kind of see the pattern here. So we have all of our times. You're going to have 30 points here because you're going to roll it from 10 centimeters 3 times. You're going to roll it from 20 centimeters 3 times for a total of 30 data points. All right. Now, we notice that if we look at this pattern here, it looks like it's curving upward. And that's because this is a quadratic relationship. All right. So when we go to edit our chart and put in a trend line, okay, so when I go to my series and I add my trend line here, it's going to try to fit a linear equation to that, but that's not what we want because this is really not linear. This is a polynomial. And it's a polynomial of order 2. That's a quadratic, all right? Now, it kind of decided that that was the right choice just based on what the data looked like, and that's about right. But we do want to use the equation for this. So we're seeing a couple things here. We see the equation, and then we'll also show our r-squared value, all right? So this has a pretty good fit. That means it fits that quadratic relationship, that equation, pretty well, and the data is following that pattern, all right? Now that equation off of this quadratic fit is really, really important. So let's go back to my presentation for just a second, all right? So what do we see? All right, well, when we do this fit, we're going to get an equation that's kind of the form y equals ax squared plus bx plus c. And we should be able to get the acceleration from this equation, but how do we do that? Well, this equation actually matches one of the kinematics equations that we already have, all right? So the equation that we have that is a quadratic is the one that we were doing in class and we found is the only one that ends up as a quadratic. It's this one. We call this a position function. And if we look at this equation, what we see is that the position, x, is a function of the time, t. And that's exactly what we have in our picture right over here. Our displacement is a function of our time. So the equation that we get from our graph there is actually telling us this equation right here. So what do we do with it? How do we get the acceleration from this? All right. We've graphed our displacements, we've graphed our times. How do we turn this into a value for our acceleration? All right, so the a term in our equation, if I go back to my graph, all right, so we see that I have 1.29 minus 0.671x plus 1.07x squared. I think this is right. So 1.29 minus 0.67x plus 1.02x squared. So take a look at this. This is what we have. We have things lining up here, right? So instead of x, we're talking about delta t. And instead of x squared, we're talking about t squared. So these terms match up with the equation exactly the way it's supposed to. So where are we going to get the acceleration from? Well, it's the term that's in front of the x squared term right here, but it's not exactly that term, right? Because let's face it, this number right here is actually 1/2 times the acceleration. So 1.02 is equal to 1/2 times the real acceleration. So all I have to do to get the acceleration is just multiply by 2 for that term that's in front of the x squared, and I should get the acceleration. So if I was using the data from that graph, right, my acceleration would be 2.04 meters per second squared. So I can pull it right from that equation, but I do have to be careful because the a term, right, the term on the x squared is actually going to be only half of the number that I want, right? So 1.02 is only half a based on this equation. So that's the first place that we're going to get our acceleration from, and that's important because we are going to compare the acceleration from this graph with the acceleration from the velocity versus time graph. All right. So when you do your graph here and you're looking at your equation, this term in front of the x squared, that's going to be 1/2 of the acceleration. So we double it. All right. So in the next video, we'll talk a little bit about the velocity versus time graph.